Welcome to this video from Derby Physics Tuition, and I've been working with a student, an A-level physics student, studying the OCR specification, and we've been looking at potential dividers. This is one of the questions that we looked at. This is question 17, paper 2, 2020, and this potential divider question actually starts off with a bit of quantum physics for part A, and we have a light emitting diode emits red light when it's positively biased and has a potential difference greater than about 1.8 volts. So basically what that's saying is that the LED will come on when the potential difference across it is greater than 1.8 volts. And you're told that the energy of a photon of red light is about 1.8 electron volts, and calculate the wavelength of this red light. So the energy of a photon is given by hf, and E is the energy of the photon, h is Planck's constant, f is the frequency, and the frequency can also be written as the speed of light divided by the wavelength, which is what we're trying to find out. So we'll substitute in c over lambda instead of f. Okay, so we now need to calculate what lambda is, so let's just rearrange that first. So lambda will be hc over the energy of the photon. Now h is Planck's constant, which will be in your data book, c is the speed of light, and E is the energy of the photon. So can we get the energy from the information in the question? Well, we're told that the energy of a photon of red light is about 1.8 electron volts. So we need to convert that value into joules. So I'll do that over here. 1.8 electron volts is 1.8 and times 1.6 times 10 to the minus 19 joules. So 1 electron volt is worth 1.6 times 10 to the minus 19 joules, and we've got 1.8 electron volts, so that will be equal to 2.88 times 10 to the minus 19 joules. So we've now got the energy of the photon, and we'll put that into the equation over here. Planck's constant from the data book, the speed of light in a vacuum from the data book, and the energy, which we've just calculated, is 2.88 times 10 to the minus 19. Okay, and if you calculate that, that gives us 6.9 times 10 to the minus 7 meters, which is what you would expect for the wavelength of a photon of visible light. Okay, and I've written the final answer to 2 significant figures because the data in the question, the minimum number of significant figures used was 2. Okay, part B of this question is the LED is connected into a circuit, so the LED that we were looking at in part A, and the battery has an EMF of 4.5 volts, and we can ignore any internal resistance, and the resistor has a value of 150 ohms, so we'll write that in there, and the potential difference across the LED is 1.8 volts, so I'll squeeze that in there. Okay, and it says calculate the ratio of the power dissipated by the LED divided by the power dissipated by the resistor. So the power dissipated, the formula we can use is that power is current times voltage. So how can we calculate the power dissipated in the resistor first of all? Okay, well, we need the current, and if the EMF is 4.5 and the potential difference across the LED is 1.8, then we've got that the potential difference across the resistor is 2.7 volts. So we can calculate the current flowing through the resistor by using I equals V over R, which is 2.7 divided by the resistance of the resistor, which is 0.018 amps. Okay, now because those two devices, the resistor and the LED, are in series, the current flowing through them will be the same. So the current through both components will be 0.018 amps. So the power dissipated by the LED, which is current times voltage, is 0.018 times the potential difference across the LED, which is 1.8, and the power dissipated by the resistor is the same current, 0.018, and the potential difference across the resistor is 2.7. And if you calculate that, it gives you a ratio of 0.67, which is the answer that you were looking for. So basic understanding of circuit theory there. You had to calculate the current flowing by calculating the current flowing through the resistor, and because both components are in series, the current will be the same, 0.018 amps. So a little bit of thought needed there for that one, but that's quite a nice little question to test your understanding of circuit theory. And the final part of this question, part C, is the diagram below shows a circuit designed by the student. So you've got a resistor, and here you've got your LDR and your LED, which are now in parallel with each other, and the LED is very close to and facing the light dependent resistor, and the circuit is taken into a dark room, and the student thought the LED would switch on. Instead, the LED was found to repeatedly switch on and off. Explain the behavior of the LED in this potential divider circuit. Okay, so quite a little bit of thought needed here to explain why the behavior of the circuit is that the LED flashes on and off rather than just staying on. So what's the first thing that's going to happen when you take the circuit into a dark room? Because there's less light, the resistance of the LDR will increase. So the resistance of the LDR is high. Okay, and if we use our V equals IR equation, if the resistance of the LDR increases, the potential difference across the LDR will increase, and because the LED is in parallel, the potential difference across the LED will increase as well. Okay, now because the resistance of the LDR has increased, then more current will flow through the LED. So more current I is flowing through the LED, and that causes the LED to switch on. Now the fact that the LED switches on is what is the key to this, because the light from the LED will enter the LDR. So the LED switched on, the light that's emitted from the LED will enter the LDR. the light dependent resistor, and so the resistance of the LDR goes down. And if the resistance of the LDR goes down, then the LED will turn off. Okay, so basically the light from the LED will be causing the resistance of the LDR to go down, and that in turn results in the LED turning off. Okay, and then this cycle will repeat itself, and the student found that the LED switches on and off. So quite a tricky, unusual question there.